Hi, welcome to Module 7 of Lecture 12, the last module of Lecture 12, and the last module of the entire part of the course on linear algebra. In the previous two modules, we dealt with issues involving Markov chains and stochastic processes in a very general way, talking about sort of the conceptual basis of these things. Here we're going to do a little practice in actually computing steady states for Markov processes, which will also help you understand a little better path dependence and history dependence. Okay, so let's start. Now, if you think back to a couple of modules ago, we talked about how you can represent a finite discrete time Markov process, or Markov chain, by using vectors and matrices, which explains why this part of this little section on stochastic processes occurs in this part of the course. So if you recall, you have a transition matrix, T, it's called M in the book, doesn't make much of a difference. It's a matrix, and here is a vector, we'll call it S for state vector, at some time t, and that's going to become some other state vector as a column vector at time t plus 1. And the idea, if you recall, was the state vector encoded information about the state. We're going to stick with two-dimensional state vectors here. You can do more, it just gets more complicated. And if you recall from the first half of this lecture, dealing with 3x3 became more tricky when you're trying to figure out things like eigenvectors, which is essentially what we're going to be doing here. But okay. So here's a state vector. You could do conflict and not conflict. This state vector that we refer to as state of conflict, where everything is in the chance of being in state A, the conflict state is 1. The chance of being in state B is 0. Note that the column must add to 1 because you have to be somewhere. Vectors. This would be a state of non-conflict, and this, importantly, would be a state in which you're half chance of having conflict and a half chance of having no conflict. Okay. Now we need to represent, and again, we can do that because it's a stochastic process, and fundamentally we're dealing with uncertainty here, with probability, and we're not sure which state we're in at the beginning. There's a half chance we could be in one state and a half chance we're in the other state. There you go. Now we need a transition matrix here. This would be 2 by 2 because it's got to take a two-dimensional column vector and turn it into a two-dimensional column vector, so it has to be 2 by 2. Now, if you think back to the early parts of this this part of the course, so now the key, if you recall from the couple modules ago, is that each column must add to 1. The reason is everything must go somewhere, since let's do this one. Since the first element of this state vector is going to be 1/4 times 1 plus 3/4 times 0, right? And then the next one is going to be 3/4 times 1 plus 1/4 times 0. The 1 ends up being multiplied by both 1/4 and 3/4. What those mean, substantively, is the chance of transitioning from the state 1 to the other, to itself. To one of the two states. Let's do that again. Let's write this out in general to remind you. Here are the elements of the transition matrix. And recall that T12 was the chance of transitioning from 2 to 1. Therefore, the chance of transitioning from 1 to 1 is T11, and the chance of transitioning from 1 to 2 is T21. Together, this is the entire chance of transitioning from 1 to somewhere. Since everything in state 1, must go somewhere, the sum of all the Tj1s, T11, T21, if there were more than that, there'd be T31 and so on, the sum of everything in this column must equal 1, implying that things in state 1 go somewhere, either to state 1 again, or state 2, or if there are more states, 3, 4, 5, and so on. So we can multiply this out. We get 1/4 and 3/4. And what this would tell you is a pathwise issue. You're going from state, this state to that state, and that's a single path, a single movement along the path. Okay. Now in practice, let's just say, in practice, in an actually observed path, you actually observe the outcome of these probabilities, right? You don't observe half-half, you observe conflict and no conflict. the issue is when taking ex ante, when looking ex ante at the future evolution of your stochastic process, what you're doing is guessing the chance of being in state A and state B. You started in the state of conflict here, state A, and given that, and given what you know the transition matrix to be, you believe that in the next period, ex ante, there'd be a 1/4 chance of staying in conflict and a 3/4 chance of being in peace and no conflict. That's ex ante. Ex post, you will realize the state you're in. You'll be in one or the other state, right? But ex ante, you assign probabilities. So looking way ahead in the distance, you're assigning probabilities to being in each individual state based on a series of events that are going to happen, a series of transitions over many, many periods. So this is sort of review from the previous parts. The new part we're going to talk about is how to figure out what the steady state is, right? What is the state at which the system no longer changes? Or rather, what's the state at which, once you're there, further transitions don't alter your probabilities, don't alter your expectations of being in each state, don't alter the distribution of possible states? Well, if you have a steady state, it's not altered by further transitions. So one way of writing that, we can call that steady state pi, which is often used. And if the transition applied to state pi leaves you in state pi, like that, that's a steady state. Well, this should look familiar to you if you went through the first half of this lecture. This is an eigenvalue equation, an eigenvector equation with eigenvalue 1. That's deliberate because an eigenvalue of 1, if you recall, meant the system is neither expanding, exploding, or contracting. It's staying constant. And that's what we want here. A steady state stays constant. So in order to figure this out, to find the steady state, we're going to have to solve this equation for pi. We're going to end up using the exact same techniques we did in the previous, when we actually solved for eigenvectors in Module 3. Before doing that, though, we have to know whether or not there actually is going to be a steady state that actually is interesting. Well, if we think back to the previous module, we can look at the theorems for ergodicity. If the stochastic process is ergodic, if the Markov train is ergodic, then it has a unique steady state from which it converges from all initial conditions. Well, to be ergodic, one definition is all states communicate. Well, you can get from state A to B over here. From B to A is over here, and from A to B is over here. So all states do communicate. You can get from A to B and B to A in one step, actually. Now, what about here? Well, there's a chance of staying in state A and a chance of staying in state B. So again, that means the system is aperiodic. The period of all states is 1, because you can stay in them immediately. Therefore, it's aperiodic, and all states communicate. Therefore, it's ergodic, and there's a unique limiting distribution, a unique steady state, from which the system converges from all initial conditions. So that's that. Now, I didn't give myself much room to write, but I'll try to do it down here in blue so it's a little clearer. Now we know there's actually an equilibrium. We can go through and actually solve this thing. Well, we have 1/4 and 3/4 and 3/4 and 1/4. Now recall, in this case, again, this is an eigenvector equation. So as before, we're not going to be able to discern the actual value of pi up to a multiplicative constant, right? If this were an eigenvector rather, so would this be, right? Because you can multiply both sides by 2 and get the second one. So we're only going to be able to figure this out up to a multiplicative constant, and we're going to find out in that case that we're not going to get 2 unique equations from this system of equations. We're going to get 1 unique equation. Recall that when we did this was by assigning one of the 2 elements to be 1. We try the first one. If it doesn't work, we'll try the second one. And that's going to have to equal 1c again. And that gives us 2 equations and one unknown. 2 of the equations are the same. We can check that. The first equation is 1/4 plus 3/4 c equals 1. The second equation is 3/4 plus 1/4 c equals c. This first one implies 3/4 c equals 3/4. This one implies 1/4 c equals 1/4. In both cases, c is 1. So we have this up here, I'm up here now, is the potential eigenvector. Now there's one problem, this adds to 2. We want all things to add to 1. So what we're going to do is translate it divided by 2, which we can do just fine because it's not defined up to a constant. And here is our steady state. The steady state has an equal chance of being in both states. Right? Note the 1/2 didn't come from anywhere in particular, right? We start off in a state of conflict, state A, at the beginning, and then we had transition. We had a 1/4 chance of staying in the state you started off in, and a 3/4 chance of switching. And it turns out, over time, if you look at this down the road, right, we expect to see ex ante a 1/2 chance of conflict and a 1/2 chance of no conflict. Okay. Now, can we play with that a little bit? Well, we can. So let's do that a little bit. What if instead we made one state sort of more likely to happen? So let's say you have a 3/4 chance of staying in state A and a 1/4 chance of moving to B, but only a 1/4 chance of staying in B and a 3/4 chance of moving from B to A. What happens then? Again, this is ergodic. You can always stay in the same state, so it's aperiodic for all states, and all states do communicate. So that's fine too. So there'll be a steady state. We can again solve this thing. We do the 1c thing again. We get 3/4 plus 3/4 c equals 1. And just to check, 1/4 plus 1/4 c equals c. I forgot to write this. This is going to be 3/4 c equals 1/4, or 1/4 c. Sorry, 3/4 c equals 1/4, same thing, makes sense. Implies c equals 1/3. Now we have 1/1/3, or this total sum is 4/3, which is more than 1, so we'll divide through by 4/3, and we get 3/4 and 1/4. Because 1/3 divided by 3/4 is 1/4. So, 1/3 divided by 4/3 is 1/4. Okay. So there we go. So in this case, we don't have a 1/2, and the reason is it's easier to move from 2 to 1, right? Because this thing up here is T1, 2, which is the chance of moving from 2 to 1. That's greater than the chance of moving from 1 to 2, which is down here. So over time, sort of probability amasses in the first state of conflict here. And you get a greater chance of being in that state than the other state. Note that even though you're generally moving towards the first state, it's easier to stay there because you do have movement to the state B, because it is a recurring state. So because non-conflict is recurring here, you don't have a 1-0 case, you have a 3/4, 1/4 case, and you do expect to see some real probability of being in the no conflict state in this case as well, even though the chance of moving to state A, the conflict state, exceeds that of moving to state B, the no conflict state. Now again, if you went on to doing 3-dimensional stuff, it would be the same. You could set up stuff kind of like this, and so on. This is a simpler one. This is a different kind of, this is a 3-state transition matrix. You see that all the columns add to 1. It should be a 0, not a 6. All the columns add to 1, so it's a valid transition matrix. Every state goes somewhere else. And this is also going to be ergodic, representing an ergodic system. You can tell that because, first of all, the diagonal ones are all non-zero, so it's aperiodic. You can stay in every state. But the all states do, well, actually, I spoke too soon. Here, if you get in state B, right, you stay in state B. So B is actually an absorbing state. And the question is, do all states communicate? Well, you can't get from B anywhere else, right? So it doesn't communicate in that case. However, it is a distinguished state because you can get to B from all other states. Because C goes to A, and then A goes to B. So you can do this one pretty easily, in fact, to check out what the actual equilibrium would be. And let's just do that because there will be an actual answer here. How do we do that? Well, we get, I should have my room here. Let's go up here. 1/6 plus 1/2 d equals 1. And 1/2 plus c equals c. And plus c equals 0. And 1/3 plus 1/2 d equals d. And we get what? We get, let's see, 5/6 times 2, that's 5/3 equals d from the first one. 5/3 over here would get you 5/6, 1/6, let's try this again. 1/3 equals 1/2 d. So d equals 2/3. What did I do wrong here? 1/2 d. So no, I'm sorry. That's 5/6. 2. What did I do wrong here? Third. D. So 1/2 d. Because 1/3. So d equals 2/3. And the first one, 1/6 plus 1/2 d equals 1. So 1/2 d equals 5/6. D equals 5/3. Ah, because you can't set the first one equal to 1. That's why. See, this is a great example of this. This does not work. You get contradictory results. So instead, we're going to now check C1d. There we go. Because it doesn't work this way. So I'm going to leave this example here instead of cutting it because it's actually a good example of when it doesn't work. So now we're going to do C1d. And let's see if I actually can just do this over again. 1/6, 1/2, 1/3. I'm going to do a different sheet here to make it clearer. There it is again. And we're going to try instead C1d because 1 didn't work in the first one. The reason is going to be it's going to be absorbing in the second one. So C1d, again, we can do this out. We get 1/6 c plus 1/2 d equals c. We get 1/2 c plus 1 equals 1. That implies c equals 0. Then we get 1/3 c plus 1/2 d equals d. With c0, this implies d equals 0. And that implies 1 equals 1, so everything works out fine if those are 0. So the steady state is 0, 1, 0, which makes sense because the second state is absorbing and nothing else is. So I apologize if that's confusing people. Could I take some time to pause there and look at that? But the reason I kept this in the video instead of cutting it, I've been messing up the initial case, is it gives you finally gives you an example of what to do when putting a 1 in the first element doesn't work. You move to the second element and look, it works. So there you go. This is the only steady state of the system. It's the absorbing state in which everything goes into state B. And the reason that works that way is because state 3 here, right, this is T13, which is the chance of going from 3 to 1. So you can go from 3 to state 1 and stay in 3. Whenever you go to 1, you can go to 3, stay in 1, go to 3, or go to 2. Once you go to 2, you're stuck there. So eventually, all the probability of the system moves towards the second state until it's absorbing completely and the state in the limit ends up there. So this is an ergodic system with an absorbing state. Right? It's a unique steady state, and it's absorbing. Okay. So that covers that. Before finishing this part, I'll show you a couple examples of what happens when you do not have an ergodic system. These are actually from the book. So first, consider the matrix. This is actually a permutation matrix. It flips the rows and columns. How does this work? Well, this does is if this is, say, A, and this is 1 minus A, then it ends up making this 1 minus A and this A. Right, so they flip. This goes on forever, right? In every single period, the state will flip. The chance of being in state A will become the chance of being in state B, and vice versa, forever. This never ever settles down to anything. This has no it doesn't settle down by itself. The only way to get a steady state out of this thing is to make a and 1 minus a equal. So when you flip them, nothing happens. And that implies that a equals a half. So if you start at a half, you stay at a half forever. So there is a steady state here, a unique steady state, but it does not converge from every single element. It converges only from the initial state of a half. So there is a unique steady state, but the system does not converge to that unique steady state from any initial condition but the steady state itself. Right? It only converges to the steady state from a half. How can we have seen this? Well, know that even though both states communicate, you can go from A to B, you have to go from A to B immediately. The system is not aperiodic. There's no chance of staying in the state you're in now. So there's that one. And in general, if you have an aperiodic system, if you have a non-aperiodic system, you can have steady states, but you just don't necessarily converge from there. Okay. Second example is the simplest example you see, the identity matrix. The identity matrix represents the ultimate in history dependence. If you start here, you end there. Every single vector in the universe, every single state vector is a steady state of the identity matrix because nothing ever changes under operation by the identity matrix. Nothing's happening. So this is completely history dependent. Whatever initial distribution you start with, that's your steady state. So it's entirely dependent on the initial conditions, history dependence, and nothing else matters at all. Okay. And there you go. That's it. That covers in this part of this course, which consists of, we started off talking about matrices and vectors and how to manipulate them and so on, some major properties of these things. We moved on to doing some more conceptual matters in linear algebra, linear independence, and spanning vectors and so on. And then we moved on in this last lecture to consider some more advanced topics on eigenvalues and eigenvectors and Markov chains and so on. Now, there's obviously much more you can learn about linear algebra out there, but this is actually a pretty good coverage of the major topics you're going to see going on in classes, plus some stuff you see in more advanced classes. Okay. That's it. And the very last part of the class now, which might not be the one you're going to now if you decided to do this earlier, will be multivariable calculus. We'll put together a bunch of stuff we've done in all of the previous parts. Thank you very much.